In October 2019, a machine finished a calculation, 200 seconds. That same calculation handed to the most powerful classical supercomputer on Earth would still be running 10,000 years from now. Your great-great-grandchildren's great-great-grandchildren would not live to see the answer. And the strangest part is not the speed. The strangest part is that nobody can fully explain where the computation happened. Not Google, not IBM, not the physicists who built the thing. There is one theory that explains it. A physicist named David Deutsch proposed it in 1985 and was largely ignored right up until the hardware started proving it true. If you are new here, hit like and subscribe. Pour yourself something warm. Get comfortable. Because tonight I am walking you through exactly what these machines mean. Why the computation happening inside them is far stranger than anyone is saying out loud, and why the universe itself may have left us a clue in the one place we forgot to look. Now let's ease into this. Part 1. The result that broke reality. There's a machine sitting in a laboratory in Santa Barbara, California, that completed a calculation in 200 seconds that would take the most powerful classical supercompute on Earth approximately 10,000 years to finish. Let that sit for a moment. Not 10 years, not 100 years, 10,000 years, a span of time longer than all of recorded human civilization, from the first Sumerian clay tablets to the smartphone in your pocket, compressed into the time it takes you to soft boil an egg. And the team that built this machine, Google's quantum hardware division, published their results in October 2019, dropped them into the scientific literature like a stone into still water, and the ripples have not stopped spreading since. The processor was called Sycamore. It had 53 superconducting qubits, which sounds like a modest number until you understand what each one of those qubits is actually doing. And we will get to that. The task it ran was called random circuit sampling, which is exactly what it sounds like. Executing a series of quantum logic operations chosen at random, then measuring the output. It sounds almost abstract, almost designed purely as a benchmark rather than a practical application. And in a sense it was. But here is the thing about benchmarks. They tell you what a system is capable of. And what Sycamore was capable of was something that should not have been possible. Now, to be fair, IBM pushed back almost immediately. Their engineers looked at the 10,000 year estimate and said, "No, with optimized classical algorithms and enough hard drive storage, you could probably simulate that same circuit in around 2.5 days. And they were not entirely wrong. The back and forth between Google and IBM in the months following that paper was one of the more entertaining episodes in recent physics history. Two teams of brilliant people essentially arguing about how impossible the impossible thing actually was. But here is what both sides quietly agreed on. The fundamental difference in kind was real. Even IBM was not claiming that classical computers matched quantum computers at this task. They were arguing about the size of the gap, not the existence of it. And the existence of the gap is the entire story. Because what Google had demonstrated for the first time in history was a machine performing a computation for which there is no efficient classical explanation. Not a slow classical explanation that could be sped up. Not an approximate classical simulation that could be refined. An actual concrete measurable case where a quantum processor did something that classical physics operating on classical matter following classical rules cannot replicate in any practical sense. The machine worked in a way the universe, according to our conventional understanding of it, should not allow. Then came Google Willow, announced in December 2024. And if Sycamore cracked the wall, Willow put a fist through it, the Willow chip demonstrated something that the entire field of quantum computing had been chasing for 30 years as a theoretical target. Scalable quantum error. Correction, specifically, it showed that as you increase the number of physical qubits used to encode a single logical qubit, the error rate does not stay constant and it does not increase. It drops exponentially. The more components you add to the system, the more stable the system becomes. Stop and think about what that means in classical engineering terms, in every system you've ever encountered in your life. Adding more components means adding more potential failure points. Your car has more parts than your bicycle and breaks down in more ways. A city power grid has more failure modes than a single generator. A human body has more ways to malfunction than a single cell. This is not a design flaw, this is entropy. This is the second law of thermodynamics expressing itself through every piece of technology ever built. More complexity equals more fragility. That is the rule. Willow broke the rule. Below a certain threshold of physical error rate. Below what physicists call the fault tolerance threshold, adding more qubits actively corrects for the errors that already exist in the system. The noise does not accumulate, the noise cancels, the machine gets more reliable as it gets bigger. And every physicist who has spent any serious time with this result knows, even if they are careful about how they say it publicly, that this behavior is not fully explained by our current models of what computation is or where it happens. This is the central tension that this entire story is built around. And it is worth naming it clearly right now so you carry it with you. We have built machines that work. We can describe with great precision how to build them, how to operate them, how to program them, how to read their outputs. What we cannot fully describe, what no one on Earth can fully describe with confidence, is why they work. Not in the deep sense, not in the sense of pointing at a physical mechanism and saying that is where the computation lives. That is the resource being consumed. That is the part of reality being asked to do the work. The machine works. That is not the mystery. The mystery is why. And that mystery threads all the way back to a paper published in 1985 by a physicist at Oxford who made a claim so radical that most of his colleagues either ignored it, dismissed it, or quietly filed it under interesting but unprovable. His claim was this: a quantum computer cannot operate within a single universe. The computation by physical necessity has to be distributed across parallel versions of reality, not as a metaphor, not as a convenient mathematical fiction, as a literal description of where the work is being done. That paper was written almost 40 years before Google Willow existed, and the data coming out of quantum hardware laboratories in 2024 looks disturbingly consistent with what he predicted. So the question is not really whether quantum computers are powerful. The question is whether we have accidentally built a device that proves the multiverse is real. And that question, once you actually sit with the evidence, is not as easy to dismiss as you might hope. Part 2. The refrigerator that shouldn't exist. Before we can talk about parallel universes and the nature of reality, we need to talk about a refrigerator, not the one in your kitchen, something altogether stranger. Something that if you walked into the room where it operates and somehow survived the experience without your instruments, would register as the coldest place you had ever stood. Colder in fact than almost anywhere in the observable cosmos. The devices used to run superconducting quantum processes like Sycamore and Willow operate at temperatures around 20 milliliters. That is 20,000 of a degree above absolute zero. For context, absolute zero. the temperature at which all thermal motion in matter theoretically ceases, is minus 273.15 degrees. The surface of the Moon on its dark side gets down to around minus 230 degrees. The cosmic microwave background radiation, the faint thermal glow left over from the Big Bang that fills the entire universe in every direction, sits at about 2.7 Kelvin, or roughly minus 270 degrees literal sense, colder than the average temperature of outer space. The structure of one of these refrigerators looks nothing like what the word suggests. It is a series of cylindrical stages suspended from the ceiling, each one colder than the one above it, dropping in temperature in stages from around 50 Kelvin at the outer shield to 4 Kelvin in the next stage, to around 800 milliliters, then 100 milliliters, and finally down to that operational floor of 20 milliliters at the core. The whole assembly is housed in a cylindrical vacuum chamber lined with gold-plated copper shielding, and it hangs like a chandelier made by engineers who took a wrong turn into a fever dream. Microwave cables run down through the stages like neural pathways, carrying the pulses that talk to the qubits at the bottom. Those qubits, in the case of superconducting processes, are built around something called a Josephson junction. A Josephson junction is essentially two superconducting materials separated by an extremely thin insulating layer, so thin that quantum mechanical tunneling can occur across it. Electrons, or more precisely Cooper, pairs of electrons can pass through the barrier without going over it, a phenomenon that has no analogue in classical physics. When you cool these junctions to near absolute zero and run them at the right operating parameters, they behave like artificial atoms. They have discrete energy levels. They respond to microwave pulses in controlled ways. And critically, they can be placed in quantum superposition. Now, here's where the language we use in everyday life starts to fail us, and we need to be careful. You've almost certainly heard the phrase that a qubit can be 0 and 1 at the same time. That is technically true, but it is also slightly misleading in a way that matters. A qubit in superposition is not like a coin spinning in the air, secretly either heads or tails, but just not revealed yet. It is genuinely in a combination of both states described by what physicists call a probability amplitude, a complex number that encodes both the likelihood of each outcome and something called the phase, which determines how different superpositions interfere with each other. This phase and interference business is not a side detail. It is the whole game. Quantum computation is not at its core about storing more information in a single bit. It is about exploiting the way probability amplitudes interfere, amplifying computational paths that lead to correct answers, cancelling paths that lead to wrong ones. The machine is not guessing faster. The machine is navigating a probability space using wave-like interference in a way that has no classical equivalent. A useful metaphor is noise-cancelling headphones, which work by producing a sound wave that is the mirror image of the ambient noise, causing the two to cancel. Quantum algorithms do something analogous with probability amplitudes. They are designed to make wrong answers destructively interfere with each other and right answers constructively reinforce. But all of this only works if the quantum states stay coherent. If the delicate superpositions and phase relationships are maintained long enough for the computation to complete. And this is where the engineering challenge becomes almost comical in its difficulty. Quantum states are extraordinarily sensitive to disturbance. A single stray photon from room temperature thermal radiation, a vibration transmitted through the floor from a passing truck outside, electromagnetic interference from a nearby phone or power line, any of these can cause what is called decoherence, the collapse of the quantum state into a classical one, destroying the computation in progress. This is why the refrigerators exist. This is why the gold-plated shielding exists. This is why quantum computing laboratories are some of the most carefully isolated environments ever built by human hands. You're trying to maintain in a physical system made of real matter quantum states that the universe itself is constantly trying to destroy. The act of observation in the quantum mechanical sense, which includes any interaction with the environment, not just a human. Looking is fatal to the computation. You're building something that can only exist in almost perfect isolation from the rest of reality. And yet against all of this, the machines work, the states hold long enough, the computations complete, and with Willow, they're getting more stable as the systems get larger, which is the opposite of what every engineering instinct says should happen. When you add more physical qubits, you're adding more matter, more potential coupling to the environment, more surface area for noise to enter the system. The laws of thermodynamics suggest this should make things worse. The data says it makes things better. There is a version of this story where that is just clever engineering, where the error correction codes being implemented are simply very good and the below threshold behavior is an expected theoretical result playing out in practice. And that version might be correct, but it sits beside another version, one that physicists like David Deutsch have been arguing for since 1985, which says the stability arises not because of what the system is doing within a single universe, but because of what it is doing across many of them simultaneously. In that version, the reason the machine works at all, the reason it resists decoherence, the reason adding more qubits stabilizes rather than destabilizes is that the computational load is being distributed across parallel branches of reality, and the error correction is in some sense a form of quantum averaging across those branches. That is a claim with enormous implications, but before you dismiss it, you need to understand the mathematics that forced a physicist in 1985 to arrive at it, because the arithmetic of quantum computing done carefully leads you somewhere that the observable universe simply cannot contain. Part 3. The arithmetic that breaks the universe. Let us do some mathematics together. Nothing complicated. Just multiplication and some honest accounting, because the most unsettling thing about quantum computing is not the hardware. It is the numbers. And the numbers, once you follow them to their conclusion, leave you with a choice between two explanations. And neither one is particularly comfortable. Start here. A classical computer stores information in bits. Each bit is either 0 or 1. 2 bits can represent 4 possible states: 0, 0, 0, 1, 1, 0, 1, 1. 3 bits can represent 8 states. The number of states a classical system can represent scales linearly with the number of bits in a simple sense. Every bit you add doubles the number of possible states. With 10 bits, you have 1024. Possible states. With 50 bits, you have over 1 quadrillion possible states. The machine, of course, exists in only one of those states at any given moment. It can move between them, process them sequentially, but it inhabits one at a time. A quantum computer does something fundamentally different. A single qubit in superposition does not represent just 0 or 1. It represents a combination of both, described by those probability amplitudes we discussed. 2 qubits in superposition represent all 4. 2-bit states simultaneously. 3 qubits represent all 8 3-bit states simultaneously. 10 qubits represent all 1024 states simultaneously. 50 qubits represent all 1 quadrillion states simultaneously. The system does not move between these states sequentially. It inhabits all of them at once. operates on all of them in parallel, and produces its output through interference. Now extend this to 300 qubits. 2 circumflex of 300 is approximately 2 asterisk 10 circumflex of 90. That is a 2 followed by 90 zeros. This is the number of states that a 300-qubit quantum computer exists in simultaneously. And here is where the accounting problem begins. The total number of atoms in the observable universe is estimated at around 10 to the circumflex of 80. 10 circumflex the 80. A 300-qubit quantum processor operating in full superposition would be simultaneously manipulating a number of states that exceeds the total number of atoms in everything we can see in any direction, from any point in space to the edge of the observable cosmos. A 300-qubit system, 300. Google Willow has 105 physical qubits. IBM's roadmap targets thousands of qubits within this decade. People are talking seriously about million-qubit systems within 20 years. The state space these systems would inhabit makes 300 qubits look like a rounding error. Now, this is the point where someone usually raises an objection, and it is a fair one. So, let us address it directly. You might say the system is not actually storing all those states simultaneously in the way a classical memory stores data. The probability amplitudes are not physical objects sitting in physical locations. The computation is a mathematical description of quantum evolution, and when you measure it, you get one answer. So where is the paradox? The paradox is this: the computation demonstrably takes place. The interference between all these states demonstrably occurs. The correct answer emerges from a process that, if it were classical, would require examining an astronomical number of possibilities in parallel. The machine produces results that can only be explained by something that was at some stage in the process simultaneously evaluating an exponentially large space of possibilities. You cannot get those results from a process that was only ever in one state at a time. The mathematics of how the output was produced requires that the intermediate steps involve something operating across the entire superposition simultaneously, so the question is not whether the system was in all those states. The mathematics of quantum mechanics requires that it was. The question is what physical substrate was hosting that information. Where was it? In a system of 300 qubits. The state space exceeds the information capacity of every atom in the observable universe. You cannot store 2 asterisk 10 circumflex the 90 amplitudes in 10 circumflex the 80 atoms. The arithmetic literally does not work. You run out of universe before you run out of states. Physicists have a name for the mathematical space in which quantum states live. It is called Hilbert space. And Hilbert space is in a very precise sense larger than physical space. It is not a metaphor. It is a mathematical fact that the space required to fully describe a quantum system of moderate size exceeds the dimensionality of any physical space we've ever observed or measured. The computation is taking place in a space that is bigger than the universe. So, where is it? This is not a rhetorical question. This is a genuine, open, actively debated question in the foundations of physics. And the person who pushed hardest on this question, who refused to treat it as merely philosophical and insisted it had a definitive physical answer, was a physicist named David Deutsch. He asked this question in 1985, before quantum computers existed as anything other than theoretical objects. He asked it with the rigorous tools of theoretical physics, and the answer he arrived at was one that the scientific community has been wrestling with ever since. If the information cannot be stored in this universe, there is only one alternative. It is being stored somewhere else. Part 4. the physicist, everyone ignored. In 1985, a young physicist at the University of Oxford named David Deutsch published a paper in the Proceedings of the Royal Society of London. The title was Quantum Theory, the Church-Turing Principle and the Universal Quantum Computer. It is one of the most important papers in the history of computer science. It is also for a long time one of the most ignored, not because it was wrong, because it was too right in a direction that most physicists were not prepared to go. Deutsch's central claim in that paper was deceptively simple. He argued that a quantum computer, by the nature of what it does, cannot be performing its computation within a single universe. The exponential resource requirement, the one we just walked through, makes it physically impossible. The information being processed, the simultaneous evaluation of exponentially many possibilities, requires a physical substrate. That substrate cannot be the matter in our observable universe. Therefore, the substrate must be elsewhere. And the only coherent physical picture in which elsewhere makes sense, Deutsch argued, is the many worlds interpretation of quantum mechanics. To understand why Deutsch arrived there, you need to understand the physics he was drawing on, which goes back almost 30 years earlier to a graduate student at Princeton named Hugh Everett III. Everett was working on his doctoral thesis in 1957, supervised by John Wheeler, and he was trying to solve a problem that had been nagging at quantum mechanics since its founding. The problem is called the measurement problem. In standard quantum mechanics, as formulated by people like Niels Bohr and Vera Heisenberg in the 1920s, quantum systems evolve in superposition according to Schrödinger's equations, smoothly deterministically following precise mathematical rules until they are measured. At the moment of measurement, the superposition collapses. One outcome is selected. The probability amplitudes for all other outcomes vanish. This is called wave function collapse. The problem is that wave function collapse is not described by Schrödinger's equation. It is a separate postulate added to the theory, not because it follows from the mathematics, but because it matches what we observe here. Every time you measure a quantum system, you see one outcome. So the collapse must happen, but the equation says no such thing. The equation says the superposition continues evolving, branching, never collapsing. Something is wrong or something is incomplete. And every physicist who has ever worked seriously on the foundations of quantum mechanics knows it. Everett's solution was radical in its simplicity. He said, what if the equation is right? What if there is no collapse? What if when a quantum measurement occurs, every possible outcome actually happens? Not sequentially, not probabilistically in the sense that one wins and others vanish, but all of them simultaneously in parallel branches of a universal wave function that never collapses. The measuring device, the experimenter, the laboratory, the planet, the galaxy. All of it branches into separate versions, one for each possible outcome, each version real, each one unaware of the others because the branches do not interact. This is the many worlds interpretation, also called the Everett interpretation, and in 1957 it was received about as warmly as you would expect. Niels Bohr, the towering patriarch of quantum mechanics, had spent 3 decades establishing what became known as the Copenhagen interpretation, the view that quantum mechanics is a tool for predicting measurement outcomes, not a description of reality, and that asking questions about what exists between measurements is meaningless. Bohr's intellectual influence over the physics community in the mid-20th century was enormous, and his dismissal of anything that tried to say but what is actually happening was essentially final. Everett's thesis was cut down, forced into a shorter and less ambitious form, and published in a journal where it attracted almost no attention. Everett left academic physics entirely. He went to work for the Pentagon, working on nuclear strategy and operations research during the Cold War. He became, by most accounts, a deeply unhappy man who drank too much and died of a heart attack in 1982 at the age of 51. He never saw his idea rehabilitated. He never knew that it would become decades later one of the most seriously discussed frameworks in the foundations of physics, taken as not merely possible but as arguably the most conservative interpretation of quantum mechanics, the one that simply takes the mathematics at face value without adding any extra postulates. David Deutsch knew about Everett. He took Everett's framework with full seriousness, not as a philosophical option among many, but as the literal physical picture of what quantum mechanics is describing. And when he sat down to analyze what a quantum computer would actually be doing, the many worlds picture was not just consistent with the result, it was required by it. A quantum computation in Deutsch's analysis is interference between parallel computations running simultaneously in parallel branches of the wave function. The reason the machine can evaluate an exponentially large problem space is that the exponentially many evaluations are distributed across exponentially many parallel realities. Each branch does a small piece of work. The interference between branches produces the answer. You collect the result in your branch, but the labor was done everywhere. This is not a small claim. Deutsch was not saying the many worlds interpretation is an interesting philosophical option. He was saying that the operational behavior of quantum computers is only explicable if you take many worlds seriously as a physical description of what is happening. He was saying that the hardware when it runs is proof that the branching is real, that other universes are not just possible or mathematical. They are load-bearing. They're doing actual computational work. And here is what makes this story so strange and so compelling. When Deutsch published that in 1985 quantum computers did not exist, they were theoretical. Sycamore and Willow were decades away. He was making a prediction about what these machines would imply about reality before anyone had actually built one. Now we have built them. Now they are running and they're doing exactly what his framework predicted, performing computations that exceed the physical resources of any single universe. The man most of his colleagues ignored in 1985 was quietly, patiently right. But we are still in the territory of interpretation, still in the space where you could, if you were determined enough, find alternative frameworks that do not require committing to the existence of parallel universes. So let us talk about the experimental evidence, because in 2022 the Nobel Committee awarded physics' highest honor to 3 people whose work taken together closes most of the philosophical exits from Deutsch's conclusion. Part 5, the Nobel that quietly confirmed it. In October 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 experimentalists. Alla Aspect of the University of Paris SLA, John Clauser of J.F. Clauser and Associates, and Anton Zerlinger of the University of Vienna. The press release described the prize as being awarded for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. That is a perfectly accurate description. It is also, if you understand what Bell inequalities are and what violating them means, one of the most consequential sentences ever written in a Nobel announcement. To understand why, you need to go back to 1964 and a paper by the Irish physicist John Stuart Bell. Bell was working at CERN and he was trying to resolve a dispute that had been simmering in physics since 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen published what became known as the EPR paper. Einstein's complaint was with what he called spooky action at a distance, the apparent implication of quantum mechanics that measuring one particle could instantaneously affect the state of a distant entangled particle regardless of the distance between them. Einstein found this unacceptable. He believed that quantum mechanics as then formulated was incomplete. He thought there had to be hidden variables, some deeper layer of physical reality, some local information carried by the particles themselves that determine their measurement outcomes in advance. In his picture, the apparent spookiness was just ignorance. The particles already knew what they would do. We just did not have access to that information yet. Bellel showed in his 1964 paper that this intuition, however reasonable it sounds, makes a testable prediction. If particles carry hidden variables that determine their measurement outcomes locally, then the correlations between measurements on distant entangled particles must obey certain mathematical limits. These limits are what we call Bell inequalities. And here is the critical thing: quantum mechanics predicts those limits will be violated. The two theories make different numerical predictions about what you will see when you measure entangled particles at two distant detectors. Bell had turned a philosophical argument into a physics experiment. The first serious experimental test came in 1972 from Clauser and his collaborator Stuart Friedman. Their results favoured quantum mechanics over hidden variables, but the experiment had loopholes, technical issues with detector efficiency, and the timing of measurements that meant a sufficiently creative advocate for hidden variables could still wiggle free. It took almost another decade before Alana Speck, working in Paris in the early 1980s, ran a series of experiments specifically designed to close the most important of those loopholes. Aspect's results, published in 1981 and 1982, violated Bell inequalities with very high statistical significance. Hidden variables, at least the local kind, were in serious trouble. But the debate did not fully settle until a set of loophole-free experiments in 2015, most notably one conducted by Ronald Hansen's group at Delft University. These experiments closed both the detection loophole and the locality loophole simultaneously using entangled electrons separated by more than a kilometre, with measurements made fast enough that no signal travelling at the speed of light could have passed between the detectors before both measurements were complete. The result Bell inequalities violated again decisively without the exit that earlier experiments had left open. The conclusion of this 30-year experimental program, the conclusion that earned Aspect, Clauser, and Zeilinger their Nobel Prize, is this: local hidden variable theories are ruled out. The particles do not carry pre-existing answers. There is no deeper classical reality underneath quantum mechanics in which everything is secretly determined in advance. The universe at its most fundamental level does not work the way Einstein hoped it did. The correlations between entangled particles are real. They are non-class, and they cannot be explained by any mechanism that involves information travelling locally between the measurement sites. Now let us be careful here, because this is a point where popular science writing sometimes goes too far. The violation of Bell inequalities does not mean that measuring one entangled particle sends a signal to the other. It does not mean information travels faster than light. There is a result in quantum mechanics called the no-signaling theorem that shows you cannot use entanglement to transmit classical information instantaneously. aspects, experiments, and all the bell. Tests that followed are consistent with this. You cannot use the correlations to send a message. But the correlations are real. They are there. They exceed what any classical local model could produce. Something is connecting these particles in a way that is not mediated by any classical signal. Something about the structure of reality produces outcomes at two separated detectors that are correlated beyond any local explanation. The universe does not compute locally. That phrase matters. It means the relationship between two distant entangled particles is not maintained by any mechanism that lives in the space between them. It is a relationship that is in some fundamental sense non-local. And now here's where this loops back to the question we started with. If quantum mechanics is non-local, if the correlations between entangled particles cannot be explained by any local hidden variable, if the universe genuinely does not keep all its information in local packets, then the question of where quantum computation is happening becomes even more pressing. The machines are non-local. The resources they draw on are non-local. The correlations they exploit are not explained by any mechanism that fits inside our conventional picture of space and time. In Deutsch's framework, this non-locality is exactly what you expect. The computation is distributed across parallel branches of reality. The interference between those branches produces correlations that look non-local from within any single branch. The Nobel Prize did not vindicate Deutsch directly, but it did close off the most comfortable alternative, the one where hidden variables carry the information locally, where there is a classical story underneath the quantum one. That story is experimentally ruled out, and the stories that remain are stranger. What remains is entanglement as a genuine physical resource, something real, something that can be maintained over arbitrary distances, something that when you scale it up becomes the engine that makes quantum computers run. But where exactly does that resource live? How far can it stretch? In 2017, a satellite answered that question in a way that should have made more headlines than it did. Part 6. The verification collapse. There is a problem that quantum computing creates that almost nobody is talking about loudly enough, and it cuts directly to something that human civilization has quietly depended on since the beginning of organized science. The problem is verification. The problem is that we are building machines whose outputs we cannot check. This is not a minor engineering inconvenience. It is a structural feature of what quantum computation is. When a classical computer runs a calculation, you can verify the result by running it again or by running a different algorithm that cross-checks it, or in many cases by working backward from the output. The process is auditable. There is a chain of reasoning from input to output that can in principle be inspected at every step. The history of mathematics and science is built on this capacity. Peer review works because results can be reproduced, proofs can be checked, claims can be tested. In 2020, a team of researchers, including Thomas Vidic at the California Institute of Technology, published a result in complexity theory that has not received nearly the public attention it deserves. The result is stated in a line of notation that reads MIP star equals RA, which sounds like alphabet soup until you unpack what it means. MIP star is the class of computational problems that can be verified by a classical computer interacting with two quantum provers, two quantum systems that share entanglement. RE is the class of problems that are recursively enumerable, meaning in rough terms, the class of problems that are solvable at all, including ones that take arbitrarily long. What the theorem says is that quantum entanglement gives verifiers access to a class of problems that is strictly enormously incomprehensibly larger than anything classically verifiable. The implication for quantum computing is this As quantum computers grow more powerful, the outputs they produce will increasingly lie beyond the verification capacity of any classical system. A sufficiently large quantum computation will produce results that no classical computer, no matter how large or how long it runs, can confirm or deny. The computation will be from the perspective of classical physics and oracle. A black box. You put the question in, an answer comes out, and there is no independent way to know if the answer is right. Think about what that means for science. The scientific method in its most basic form is reproducibility. An experiment must be repeatable. A result must be verifiable by independent means. A claim must be checkable. These are not just procedural preferences, they are the load-bearing assumptions of empirical knowledge. Remove them and you are no longer doing science in any meaningful sense. You're doing something else, something more like faith in a process. Now, we're not at the point yet where any quantum computer is producing results that are completely unverifiable. The systems that exist today are still small enough that their outputs can be spot-checked by classical means at significant computational cost. But the trajectory is clear. Willow's performance already pushes into regimes where full classical verification is impractical. IBM's roadmap, Google's roadmap, Microsoft's roadmap, they're all pointed at systems where verification will become impossible long before the machines reach their target. Applications. This creates a strange epistemic situation. We will have machines that can in principle solve problems of enormous practical importance. Drug discovery, material science, financial optimization, logistics, cryptography, and we will have to trust their outputs without being able to fully verify them by any independent means. The trust will have to be placed in the process, in the physics, in the theoretical framework that predicts the machine should work correctly. But the theoretical framework, quantum mechanics, is the thing whose physical interpretation we cannot agree on. You're being asked to trust the output of a machine whose operating principle is a subject of active philosophical dispute using a method that cannot be checked by the civilization that built it. That is the verification collapse, and it is coming faster than most people realize. This might sound purely like an abstract problem, but it has very concrete implications. When quantum computers are used to discover new drugs, to model molecular interactions in ways that classical computers cannot, the difference between a correct answer and a plausible-sounding wrong answer might not be detectable until the drug is in clinical trials or worse. When quantum systems are used in financial modelling, a verification gap means model errors could propagate into real economic systems before anyone catches them. And when quantum computers are eventually pointed at encryption at the mathematical structures that protect every financial transaction and sensitive communication on Earth, the verification gap cuts in a very different direction. Because there it is not that we cannot check the output. It is that the output is designed to break things we rely on. But here is the other side of this. The machines are getting more stable. The error rates are dropping. Willow's below-threshold behavior means that at system scale they are converging toward reliable, reproducible outputs, and that raises a deeper question. Why are they converging? Why, as you add more qubits, does the noise not accumulate the way it should? What is doing the stabilizing? The engineering answer error correction codes is true as far as it goes, but it does not fully answer why those codes work, why the below-threshold behavior is achievable at all, why the system behaves as if it has access to more error correction resources than any single physical system should possess. The answer to that question might require looking not just at the hardware, but at the space across which quantum correlations can operate. And that space, as it turns out, is larger than the laboratory. Much, much larger. Part 7, the error correction paradox. Quantum error correction is one of those topics that sounds like an engineering problem and turns out to be a philosophical one. Understanding why requires going back to 1995 when a mathematician and physicist named Peter Shor, yes, the same Shor, who later gave his name to the quantum algorithm that threatens all of modern encryption, published a paper showing that quantum error correction was theoretically possible at all. At the time, this was not obvious. In fact, before Shor's paper, many physicists believed that decoherence made large-scale quantum computing permanently impossible. The argument went like this: quantum states are fragile, errors accumulate, and because quantum mechanics does not allow you to simply copy a qubit the way you copy classical data, there seemed to be no way to catch and correct errors before they destroyed the computation. Shor's insight was that you could protect a logical qubit by encoding it redundantly across multiple physical qubits in a way that allowed errors to be detected and corrected without ever measuring the underlying quantum state directly. You could measure certain relationships between qubits, what are called stabilizer measurements, that tell you if an error occurred without telling you what the actual state of the qubit is. This preserves the quantum information while allowing the error to be corrected. It is a beautiful idea. The theory worked. The question was whether the hardware could ever be good, enough to make it practical. The answer required the threshold theorem, which followed shortly after. The threshold theorem says that if the error rate of individual physical qubit operations falls below a certain critical value, roughly around 1% for many architectures, though the exact number varies, then you can use quantum error correction to reduce the logical error rate, arbitrarily, essentially making the computation as reliable as you want at the cost of using more physical qubits per logical qubit. Below the threshold, more physical qubits means lower logical error rates. Above the threshold, more physical qubits means more total errors. The threshold is the critical point. Google Willow in December 2024 demonstrated the first real hardware evidence of below-threshold scaling across multiple code distances. Code distance is the measure of how many physical qubits are used per logical qubit. Willow showed that as they increased the code distance, as they used more physical qubits to encode each logical qubit, the error rate dropped, and it dropped in the exponential way the threshold theorem predicted it would for below-threshold hardware. This was the experimental confirmation of a theoretical result that had been hanging in the air since 1995. It can actually be done. But here is the paradox stated as cleanly as possible. To correct errors, you need to make measurements. To make measurements on a quantum system is to interact with it, which in general causes decoherence, which causes errors. You're using a process that introduces errors to correct errors. At first glance, this sounds circular and self-defeating. Why does it work? The answer that the formalism gives you is that the stabilizer measurements are carefully designed to extract only enough information to identify the error syndrome, the pattern of errors that has occurred without extracting any information about the logical quantum state being protected. They measure the relationships between qubits, not the qubits themselves. And because they only access the error information and not the logical information, they do not collapse the logical superposition. The error gets identified and corrected. The computation continues. This is mathematically rigorous. It works, but it depends on something subtle. The errors must be local and independent. Each physical qubit must fail on its own without the failure of one qubit causing correlated failures in others. If errors are correlated, if the noise in the system is not random but structured, then the error correction codes fail because they're designed specifically for independent random errors. Correlated errors create error patterns that look like logical errors to the syndrome measurements, and those cannot be corrected without destroying the computation. What this means is that the reason quantum error correction works, the reason Willow can achieve below-threshold behavior depends on the quantum system behaving as if each physical qubit is interacting only with its local environment, not with the entire system collectively. The noise is treated as local, the corrections are local, the codes work locally, but the quantum states being protected are not local. They're entangled, they're non-local. They're in Deutsch's framework distributed across parallel branches of reality. The computation that the error correction is protecting is at its core a non-local phenomenon that is being maintained by local operations. And that combination local error correction protecting non-local computation only works because the two kinds of dynamics operate on different timescales and through different mechanisms. The noise couples to the qubits through local physical interactions. The entanglement operates at a level that is in some sense deeper than the local physical interactions. The error correction is catching errors before they disrupt the deeper structure that the computation lives in. If that deeper structure is the universal wave function, if the computation is genuinely distributed across parallel branches, then what will demonstrated is that those branches can be kept coherent and aligned through local operations performed entirely within a single branch. You're in this interpretation doing error correction in one universe that propagates stability to computation happening across many. The below-threshold behavior is evidence not just that the engineering works, but that the structure being protected is more robust than any classical system, because it is not limited to a single physical instantiation. That is a speculative reading, but it is consistent with everything we know, and the machines are not alone in demonstrating non-class robustness. In 2017, a satellite told us that entanglement does not care about the distance between the stars. Part 8. The satellite that proves it's real. In 2017, a Chinese research satellite named Micus, named after the ancient Chinese philosopher Mosi, who performed some of the first recorded experiments in optics, was sitting in a sun-synchronous orbit approximately 500 kilometers above the Earth's surface. The satellite had been launched the previous year by a team at the Chinese Academy of Sciences led by physicist Jian Pan. Its purpose was straightforward in description and staggering in implication to distribute quantum entanglement between ground stations separated by distances that made the achievement previously unimaginable. The experiment that Michus ran in 2017 established entanglement between photons detected at two stations on the ground, one in the city of Delinga and one in Liang, separated by over 1,200 kilometers, 200 kilometers, the width of France and Germany. Combined, the distance from London to Athens, the satellite generated pairs of entangled photons and sent one photon from each pair to each ground station, and the entanglement survived. The correlations between the measurements at the two stations violated Bell inequalities by more than 11 standard deviations. There was no ambiguity. The entanglement was real. The connection held. The following year, Michus was used to conduct a quantum key distribution test between Beijing and Vienna, separated by over 7,000 km, using a chain of ground stations and the satellite as an intermediary. This was the first intercontinental quantum-secured communication. The test demonstrated that quantum cryptography, communication whose security is guaranteed by the laws of physics rather than computational difficulty, was viable at global scales. Now, why does any of this matter for the question we are building toward? Because the Micius experiment established something that the laboratory demonstrations had always suggested but never so clearly demonstrated. Entanglement does not care about distance. The quantum correlation between two photons once established is maintained regardless of the separation between the particles, 1,200 kilometers of atmosphere, of weather, of the curvature of the Earth, of relativistic effects due to orbital velocity. None of it breaks the entanglement. The relationship between those two photons persists across a scale that dwarfs any laboratory. And here is the critical implication for quantum computing. If entanglement is a resource, and it is the core resource that quantum computation exploits, then that resource is not constrained to the physical volume of the hardware that generates it. The correlations that make quantum computation possible operate over scales that have no classical analogue. There is no classical mechanism by which a property of one particle can remain perfectly correlated with a property of another particle 1,200 kilometers away, with no direct physical connection between them. No field, no wire, no signal that could travel between them in the time available. And yet the correlations are there. The no-signaling theorem tells us, as we discussed, that you cannot use this to send information faster than light. The correlations are real, but you cannot choose which correlation you observe in such a way as to encode a message at the other end. This is not a loophole in special relativity, but it is something stranger in a different way. It means that the relationship between those particles is being maintained by something that is not a physical signal passing through the space between them. The universe is maintaining a correlation without sending a message. The relationship exists without transmission. What kind of physical picture is consistent with this in the Copenhagen interpretation? You simply do not ask. The wave function is a tool for predicting measurement outcomes, and there is no real connection. There is just a mathematical correlation, and questions about the physical mechanism behind it are considered meaningless. But we've already seen that the Copenhagen interpretation's dismissal of such questions was not settled physics, but rather a methodological preference that bore enforced by force of personality. The Bell experiments and the Nobel Prize in 2022 confirm that something non-class is happening. The Micius experiments confirm it holds over planetary scales in the Everett framework. The explanation is that the two particles are part of a single global quantum state, a single wave function that encompasses both of them, regardless of their spatial separation. When you measure one particle in one branch, the corresponding particle in the entangled pair is in the correlated state in that same branch. The correlation is maintained because the two particles have never stopped being part of the same quantum state, regardless of the distance between them. Space is in this picture not the fundamental arena in which quantum events happen. Quantum states are, and quantum states do not have a location in, the way that classical objects do. This is not merely an interpretation, no. It has architectural implications for how quantum computers are built. You can in principle have components of a quantum computer that are physically separated in different buildings or one day on different continents and still exploit their entanglement for computation. The Micius experiments confirm that the entanglement survives travel through real physical environments at scales that matter for real infrastructure, and the fact that it survives without a classical signal mediating it means that the resource quantum computers are exploiting is not bound by the ordinary constraints of space. Which brings us to a theory published in 2013 that proposes something even more radical: that space itself might be created by entanglement, that the geometry of the universe might be at its deepest level a consequence of quantum connections, and that quantum computers might be in some sense Manipulating the Fabric of Spacetime Itself. Part 9. The Wormhole Interpretation. In 2013, two theoretical physicists published a paper with a title that looks like a mathematical equation: ER equals EPR. The ER stands for Einstein-Rosen, the name given to the theoretical structure better known as a wormhole, a connection between two distant regions of space-time, predicted by general relativity in a paper by Einstein and Nathan Rosen in 1935. The EPR stands for Einstein, Podolsky and Rosen, the same 1935 paper about quantum entanglement and its apparent non-locality that we discussed earlier. The authors of the 2013 paper were Juan Maldacena, one of the most cited physicists in history, and Leonard Susskind, another titan of theoretical physics. Their claim was that these two concepts, wormholes and entanglement, are not just analogous, they are the same thing. The ER equals EPR conjecture proposes that any two entangled particles are connected by a microscopic wormhole, not metaphorically, not as a mathematical curiosity, as a physical description of the structure of space-time. Entanglement in this picture is not a correlation between two particles that happens to be maintained over long distances. Entanglement is a geometric connection, a tiny non-traversable bridge in spacetime that links the two particles. The particles are not just correlated, they're connected by a thread of spacetime itself. Now, immediately, the wormholes in question are not traversable. You cannot send a signal through them. You cannot travel through them. They are not science fiction. Wormholes! They're topological connections, structures in the geometry of spacetime that link two regions without providing a pathway for information or matter to pass. This is why entanglement cannot be used for faster-than-light communication. Even in this framework, the bridge exists, but it is too small and too structured to carry anything through. The no-signaling theorem is preserved, but the implication goes much further than communication. If ER equals EPR is correct, it means that space-time geometry is not the background stage on which quantum physics happens. It means that space-time geometry is produced by quantum physics, specifically the structure of space-time. The network of connections that we experience as distances and directions is a consequence of the entanglement structure of the quantum states that make up reality. More entanglement means more connectivity. Less entanglement means the geometry pulls apart. In the limit of zero entanglement, the geometric connection disappears. Space itself dissolves. This is the idea of emergent space-time. The proposal that the three dimensions of space and one of time that we experience as the arena of all physical events are not fundamental. They are derived. They emerge from a more fundamental layer of quantum information, a layer in which the relevant variable is not position but entanglement. In this picture, asking where is the quantum computation happening is not just a question about geography. It is a question about what creates geography. What does this mean for quantum computers? A quantum computer is a network of entangled qubits. As the number of qubits increases and the entanglement structure becomes more complex, the system is in the ER equals EPR framework, generating an increasingly complex geometric structure. The processor is not just manipulating quantum states. It is in some technical sense constructing and navigating a quantum geometry. The computation that takes place inside a large quantum processor might be at a level we do not yet fully understand, a form of geometric manipulation, a rearrangement of the space-time connections encoded in the entanglement pattern of the qubits. This sounds like it should be science fiction, and the honest answer is that it is currently theoretical and experimentally unconfirmed. The ER equals EPR conjecture has not been proven from first principles. It has not been tested by a direct experiment that could falsify it. It is a proposal, an influential, mathematically sophisticated, widely discussed proposal by some of the most respected people in theoretical physics, but it remains in the domain of conjecture. Maldesner and Susskind themselves have been careful to note that the conjecture applies most cleanly in certain mathematical limits and may not translate directly to the real world in its simplest form. But physicists take it seriously not because it is proven, but because it connects. It connects quantum mechanics to general relativity. Two theories that have resisted unification for a century through the single concept of entanglement. It provides a geometric picture of why entanglement is non-local because the geometry of spacetime is produced by the entanglement structure. Non-local correlations are not puzzling. They are the entanglement structure expressing itself, and it points at a possible answer to the deepest question in physics. What is gravity, and how does it fit with quantum mechanics if the ER equals EPR conjecture is correct? Then quantum computers are not just calculating tools, they are engines that construct and traverse geometric structures in a space that underlies the spacetime we observe. The computation that Sycamore performed in 200 seconds was not just a quantum calculation. It was a navigation of a geometry that exists at a layer of reality below space and time. And the reason it could not be simulated is not just that it required too many states. It is that the geometric structure it traversed has no classical description. But even this might not be the deepest layer, because before there was spacetime, before there were particles, before there were quantum fields, there may be something more fundamental still, something that a physicist who spent his career straddling quantum mechanics and general relativity spent his final decades trying to name. Part 10. The information layer beneath reality. John Archibald Wheeler was one of the most influential American physicists of the 20th century. He coined the term black hole. He worked with Niels Bohr on nuclear fission. He was Richard Feynman's doctoral advisor. He was one of those rare people who combined exceptional technical skill with a genuine appetite for the deepest possible questions. And late in his career, in his 70s and 80s, Wheeler became increasingly preoccupied with a single question that he eventually distilled into a 3-word phrase: it from bit. The idea behind it from bit is this: every physical thing, every particle, every field, every region of spacetime, every observable property of every system in the universe derives its existence from information, not information in the loose colloquial sense, information in the strict technical sense, binary distinctions, yes or no answers to yes or no questions. The fundamental logical structure that underlies measurement and observation. In Wheeler's view, the universe is not made of matter and energy that happens to carry information. The universe is made of information, and matter and energy are what information looks like when it takes on physical form. The it of the physical world comes from the bit of binary observation. This is a profound and deliberately strange claim. It means that the question, what is the universe made of, has an answer that is not atoms or quantum fields or strings, but rather differences, distinguishable states. The universe is made of the fact that some things are not other things, that some properties take one value rather than another, that measurement yields a definite outcome rather than ambiguity. The physical world is in this picture the system that generates and processes those distinctions. The claim is not purely philosophical. There is a physical result that points in this direction, and it is called Landau's principle. Rolf Landau, working at IBM in 1961, proposed that the eraser of information, the act of resetting a bit from an unknown state to a known one, must be accompanied by the release of a minimum amount of energy equal to the temperature times the Boltzmann constant times the natural logarithm of 2. This seems like a minor technical footnote, but it is not. It means that information erasure generates heat. It means that information processing is a physical process with physical thermodynamic consequences. Information is not just a description of physical reality. It is part of physical reality. Landau's principle was considered speculative and difficult to test for 50 years. Then, in 2012, an experiment at the University of León confirmed it directly. A team led by Sergio Schilberto used tiny colloidal particles in a controlled potential well to demonstrate that erasing one bit of information dissipates exactly the minimum amount of energy that Landau's principle predicts to within experimental error. The result has been confirmed multiple times since information eraser has a thermodynamic cost. Information has a physics. Information is physical. This connects to a concept from general relativity and black hole thermodynamics called the holographic principle. In the 1990s, work by Jacob Bekenstein, Stephen Hawking and later Jared Tuft and Susskind established that the maximum information content of any region of space is proportional not to the volume of that region but to its surface area. The boundary of a region can only encode a certain amount of information, and that information limit bounds everything that can happen inside the region. Information is not stored in the three-dimensional bulk. It lives on the two-dimensional surface. The holographic principle has its clearest formulation in the ADS-CFT correspondence, developed by Maldina in 1997, which provides a concrete mathematical duality between a theory of quantum gravity and a higher dimensional curved spacetime and a quantum field theory on the boundary of that spacetime. This is the most precisely tested duality in theoretical physics. It works, and it tells us that the three-dimensional world we experience might be in a precise technical sense a projection of information encoded on a two-dimensional surface. What does all of this mean for quantum computers if matter is information? If spacetime is information, if the structure of reality at its deepest level is the processing and encoding of binary distinctions, then a quantum computer is not a tool that processes information about reality. A quantum computer is a piece of reality doing what reality does at its most fundamental level. It is information processing information. It is the universe computing itself. The reason quantum computers can access exponentially large state spaces is not just that they use clever engineering or that they leverage non-class physics. In the information first picture, the reason is that the fundamental substrate of reality, the information layer from which space and time and matter emerge, has an exponential capacity that no classical physical system within a single branch of spacetime can match. Quantum computers tap into that capacity because they are at their operating level closer to the information layer than classical systems are. They are not running above the substrate. They are running in it. This gives Wheeler's phrase it from bit a specific operational content in the age of quantum computing, the bit from which the it comes is not a metaphor. It is the computational substrate, and quantum computers are in this reading windows into that substrate machines that make visible through their outputs and their capabilities the information theoretic structure of reality that underlies everything else. The universe may be at its deepest level a computation, and if it is, we've just built a machine that speaks its language. Part 11. Encryption is already on a timer. Let us come back to Earth for a moment, because all of this, the parallel universes, the entanglement over 1,200 kilometers, the information layer beneath reality might sound like it belongs in the realm of physics, journals, and late-night philosophy. But one of its consequences is already sitting in a government planning document near you in a competition that started in 2016 and just finished in 2024. And it has real consequences for the security of every financial transaction, every private message, every classified communication on Earth. In 2016, the National Institute of Standards and Technology, NIST, the American federal agency responsible for setting technical standards, launched a public competition. They were looking for new cryptographic algorithms to replace the ones that currently protect essentially all digital communication on Earth. The reason they needed new ones is a quantum algorithm published in 1994 by Peter Shor, the same person who proved quantum error correction was possible, which demonstrated that a sufficiently powerful quantum computer could factor large integers exponentially faster than any known classical algorithm. This matters because the security of RSA encryption, which is the foundation of most public key cryptography, rests on the hardness of factoring large numbers. To factor a number like the product of two 1000-digit primes using the best classical algorithms would take longer than the age of the universe. Shor's algorithm running on a large fault-tolerant quantum computer could do it in hours, maybe faster. The entire mathematical structure on which Internet security is built would become as trivially breakable as a padlock with a combination written on it. NIST's competition ran for 8 years, attracting hundreds of submissions from cryptographers around the world. In 2024, the final post-quantum cryptographic standards were published. The primary algorithms are crystals, Kyber for key encapsulation, crystals Dithium and Falcon for digital signatures, and Sphinx Plus as a hash-based backup option. These are all based on mathematical problems believed to be hard for quantum computers, problems involving lattice structures rather than factoring where no quantum speedup analogous to Shor's is currently known. The transition to these standards is now underway across government and finance, though it will take years to fully deploy. But here is the thing. The transition is happening now before large fault-tolerant quantum computers exist. The reason is not paranoia. The reason is a strategy called Harvest, now decrypt later. Intelligence agencies, foreign, governments, and sophisticated criminal organizations can record encrypted traffic today. Every banking transaction, every diplomatic communication, every military exchange that passes over the internet and store it. They cannot decrypt it today. But when large quantum computers become available, they will be able to retroactively decrypt everything they collected. Communications that are happening right now, secured with RSA encryption that currently requires the age of the universe to break, will become readable. The moment someone builds a Shor-capable quantum processor, the national security community takes this seriously. The transition to post-quantum cryptography in government systems is being treated as urgent, not eventual. Multiple governments have issued classified assessments of the timeline to Shor-capable quantum hardware. The fact that NIST completed its competition in 2024 and standards are being deployed in 2025 and 2026 tells you something about the internal estimates of how much time is left. How much time is actually left, nobody knows. Willow's 105 qubits are still far from the millions of physical qubits needed to run Shor's algorithm against real-world RSA key sizes. Current estimates from reputable sources suggest a Shor-capable machine is still a decade or more away. But those estimates have been wrong before, typically in the optimistic direction, meaning things took longer than expected. The field has also surprised everyone with the pace of Willow's error correction results. It would be unwise to assume the timeline is fixed. The cryptography story is important not just for what it tells us about quantum computing's near-term impact. It tells us about the broader pattern of how this technology changes things quietly, structurally before the general public notices. The encryption standards you depend on daily, the ones that protect your banking and your medical records and your private communications, are being replaced right now. Not because quantum computers have already broken them, but because the people who know the field best believe the threat is real enough to spend billions of dollars preparing for it. That is not alarmism. That is the signal. And encryption is just the beginning. Because quantum computing is not developing in isolation. It is developing alongside another technology that by itself was already the most transformative development of the early 21st century. The combination of the two opens possibilities and creates risks that neither could produce alone. Part 12. The AI and Quantum Convergence. There is a conversation happening right now in the spaces between disciplines in the hallways of research labs, where quantum physicists and machine learning engineers are starting to find themselves working on adjacent problems. And it is the kind of conversation that tends to stay inside conference rooms, rather than making it into press releases. The question being asked is deceptively simple. What happens when quantum computing and artificial intelligence stop being separate fields and start becoming a single system, not parallel? Tools applied to parallel problems, an integrated architecture where each technology amplifies the other's capabilities in ways that neither could achieve alone. The reason this question is being asked now, rather than 10 years ago, is that both technologies are maturing simultaneously, and the places where they touch are becoming visible in practical, not just theoretical ways. The most immediate and least speculative connection is already operating in laboratories today. Quantum computers, particularly the devices that represent the current state-of-the-art, which researchers call NISQ devices, short for Noisy Intermediate Scale Quantum, produce outputs that are corrupted by hardware errors and environmental noise. Extracting useful information from these outputs requires sophisticated classical post-processing. And it turns out that machine learning algorithms are remarkably good at this post-processing work. They can identify systematic patterns in noisy quantum outputs, learn to compensate for hardware-specific error signatures that vary from chip to chip, and optimize the compilation of quantum circuits in ways that human engineers had not anticipated and would likely not have found on their own. AI is already serving as a translator between quantum hardware and human-readable results. That is useful. It is also the modest end of what is coming. The more consequential direction runs the other way, using quantum computation to enhance artificial intelligence itself. To understand why this might matter, you need to know where the computational cost of modern AI actually lives. The answer is linear algebra, specifically matrix multiplication at enormous scale. Training a large language model or running inference on one requires multiplying matrices with billions or trillions of entries repeatedly across millions of training steps. The hardware that powers modern AI, the GPU clusters consuming megawatt of electricity and data centers around the world, is essentially optimized matrix multiplication machinery. It is very good at this. It is also approaching physical limits in terms of how fast and how efficiently it can be done. Classically, quantum algorithms offer a different approach. The most relevant is something called the HHL algorithm, developed in 2009 by Aram Harrow. Avanat Hasidim, and Seth Lloyd, which provides a quantum method for solving certain linear systems that offers a polynomial speedup over the best classical approaches. Polynomial speedup is not the dramatic exponential advantage you get from Shor's algorithm for factoring, but do not let that undersell it. When the operation you're speeding up is the dominant computational cost of the most expensive technology humans have ever built, a polynomial improvement translates into real acceleration at scale. If quantum hardware matures to the point where HHL and related algorithms can be run reliably on practically relevant problem sizes, the cost and time required to train and run AI systems could drop substantially. More speculatively, researchers have been exploring the possibility of using quantum hardware directly inside neural network architectures. The concept is called quantum neural networks, and the basic idea is that instead of representing network weights as classical numbers, you represent them as quantum amplitudes, instead of classical activation functions introducing nonlinearity. Measurement of quantum states does it. Instead of classical matrix operations propagating information forward through the network, quantum interference does it, in principle. A quantum neural network could represent and process certain classes of high-dimensional data more efficiently than any classical architecture, because the Hilbert space it operates in is exponentially larger than any classical vector space of comparable physical size. In practice, nobody has convincingly demonstrated this advantage on a practically relevant task yet. Current quantum hardware is too noisy and too small. The quantum neural network proposals that look good on paper tend to run into a problem called barren plateaus when you actually try to train them, where the gradient of the loss function becomes exponentially flat and training stalls. This is an active research problem and not obviously unsolvable, but it means the path from theory to working quantum-enhanced AI is not as short as the enthusiasm sometimes suggests. The honest answer is that quantum-accelerated AI is a real possibility and a genuinely open question, not a guaranteed outcome and not a dismissed one. But the connection between these two technologies that I find most interesting is not about algorithms at all. It is about something more fundamental, something that sits at the level of what it means to understand a system rather than just use it. And to see it, you need to think about what AI already is before quantum enters the picture. Large AI systems, the kind that generate text, analyze images, predict protein structures, and compose music, are already partially opaque to the people who build them. The internal representations that a large language model uses to produce its outputs are high-dimensional structures, encoding relationships between concepts in spaces of thousands or tens of thousands of dimensions. And the way those representations combine to produce any particular output is not something a human engineer can trace the way you would trace a classical algorithm. We can probe the systems from outside, we can run interpretability experiments, look for patterns, identify circuits within the network that seem to correspond to particular behaviors. But we cannot read the reasoning, we cannot follow the logic step by step the way we can with a program someone wrote intentionally. The systems work and we do not fully understand why they work, and we use them anyway. Quantum computers add a second layer of the same opacity and the two layers compound rather than simply add. The computation inside a quantum processor happens in a Hilbert space that vastly exceeds the dimensionality of anything classically describable. The interference patterns that produce the output cannot be observed directly without destroying the computation. The intermediate states are inaccessible by definition. When you read the output of a quantum computation, you're seeing the result of a process that occurred in a space you cannot examine. following dynamics you cannot simulate, exploiting correlations that have no classical description. Now, imagine a system where a classical AI, one whose internal reasoning we cannot fully interpret, designs and optimizes quantum circuits that run on quantum hardware, whose internal operation we cannot simulate. The output comes out the other end. It is useful. It might be the most useful thing anyone has ever computed. And there is no human anywhere in the loop who can tell you step by step how it got there. You have a black box built inside a black box. There's a version of this that sounds fine. We use black boxes constantly. Your immune system is a black box. The global financial system is a black box. The weather is a black box. Black boxes produce useful outputs, and we navigate around them. The point is not that black box systems are inherently dangerous. The point is that science as a method depends on being able to look inside boxes. It depends on mechanistic explanations, on being able to predict behavior in genuinely novel circumstances rather than interpolating from training data, on being able to say not just that something works, but why it works and what it will do when conditions change in ways we have not seen before. A world where our most powerful computational tools are jointly quantum and AI in ways that are opaque. From both directions is a world where the gap between capability and understanding grows wider every year, and where the feedback loop that has historically allowed technology to improve science, which improves technology, begins to weaken. And then there is the frontier that is stranger still, the one that researchers are starting to discuss in careful, hedged language in journal papers and conference talks. The question of whether quantum AI systems might discover patterns in physical reality that are not accessible to human-designed algorithms, not because the humans lack cleverness or computational power, but because the patterns themselves live in a space of quantum correlations that human intuition simply cannot navigate. Human intuition was built by evolution for a classical world. We track objects through space. We reason about causes preceding effects. We build mental models of systems we can observe. None of that equipment is calibrated for a space where particles are entangled across hundreds of kilometers, where information has no location, where the substrate of computation might be distributed across parallel branches of reality. If quantum AI systems begin operating in that space effectively, the outputs they produce may not just be computationally opaque, they may be conceptually alien. We will have answers we cannot understand to questions we barely know how to ask, and we will have to decide as a civilization what we do with answers like that. That sounds like the most speculative point in this entire story. But consider the hardware architecture most likely to enable it is being built right now. Not by Google, not by IBM, but by a team that has spent over 2 decades pursuing a fundamentally different approach to the stability problem. One that does not try to catch errors after they happen, but to make the errors structurally impossible in the first place. And the physics behind that approach turns out to connect in ways that are difficult to dismiss as coincidence to everything else we've been discussing about where quantum information actually lives. Part 13. Microsoft's topological qubit. Every quantum computing company in the world is fighting the same war, and the enemy is the universe itself. Quantum states are fragile in a way that has no classical analogue. A classical bit, a 1 or a 0 stored in a transistor, is robust. You can heat it, vibrate it, shine light on it, and it stays put. The physical system settles back into its intended state because classical states are stable attractors. Knock them, they return. Quantum states are the opposite. They're more like a soap bubble balanced on the tip of a needle than like a transistor. Any interaction with the environment, any stray photon, Any vibration transmitted through the mounting structure, any electromagnetic fluctuation from a cable a meter away collapses the superposition. The quantum information vanishes. The computation fails. Google and IBM have approached this problem the way you approach most engineering problems, with exceptional craftsmanship and clever compensating. Systems. Build the best possible superconducting qubits. Reduce the physical error rates through careful material science and circuit design. Then layer quantum error correction codes on top to catch and fix the errors that remain. It's a brute force strategy married to elegant mathematics, and it is working. Sycamore and Willow are the proof. The below-threshold error correction that Willow demonstrated in December 2024 is real progress on this roadmap. Nobody should understate that. But the roadmap has a cost that is worth being honest about. Quantum error correction requires redundancy to protect one logical qubit, the qubit that actually does the computation. You need many physical qubits encoding it spread across the hardware in a pattern designed so that errors can be detected and corrected without measuring the logical state directly. Current estimates for fault-tolerant quantum computation suggest you need somewhere between 1,000 and 10,000 physical qubits per logical qubit, depending on the architecture and the target error rate. A quantum computer powerful enough to run Shor's algorithm against real-world encryption keys would need millions of physical qubits, maybe tens of millions, all operating below the error threshold, all simultaneously maintained in a dilution refrigerator at 20 mil. The engineering challenge scales with every qubit you add. The path is real, but it is long. Microsoft has spent over 2 decades betting that there is a shorter path. Their strategy does not involve better error correction. It involves making qubits that do not need error correction in the same way because the errors cannot reach them. The approach is built around a type of exotic quasi-particle called a major zero mode. And to understand why it matters, you need to know a little about the man whose name it carries, because his story is one of the stranger ones in the history of physics. Et Majorana was an Italian theoretical physicist, widely considered a prodigy even by the standards of a generation that included Enrico Fermi and Vera Heisenberg. In 1937, he published a paper proposing that certain types of quantum particles, specifically fermions with half-integer spin, could be their own antiparticles. In normal particle physics, every particle has a corresponding antiparticle with opposite charge. An electron has a positron. A proton has an antiroton. When particle meets antiparticle, they annihilate. Majorana proposed that some particles might be symmetric in this way, equal to their own mirror image, neither particle nor antiparticle in the conventional sense, but something that is both simultaneously. The mathematical structure was elegant, the physical implications were deep. And then in March 1938, Majorana boarded a boat travelling from Palmo to Naples, was seen by other passengers, and was never seen again. No body was ever found. No definitive explanation was ever established. He was 31 years old. His physics survived him. His fate did not. Majorana's zero modes are not the particles Majorana originally described. They are quasi-particles, collective, excitations that emerge in certain condensed matter systems, particularly in topological superconductors under specific conditions. What they share with Majorana's fermions is the mathematical property of being their own conjugate. But what makes them interesting for quantum computing is something more specific. The quantum information they encode is stored non-locally. A Majorana zero mode cannot exist alone. It always comes in pairs with the two modes of the pair spatially separated from each other. And the quantum information The logical state of the qubit is not stored in either mode individually. It is stored in the correlation between the two. It lives in the relationship, not in either of the members of the relationship. This is the feature that Microsoft has been chasing for 2 decades. And the reason is straightforward once you see it. If the information is not located in any single place, then local disturbances cannot destroy it. A vibration here cannot access information that is not here. Stray photon there cannot flip a bit that is not there. To corrupt the information, you would have to simultaneously disturb both modes of the pair in a correlated way, which requires a very specific kind of noise that random thermal fluctuations essentially never produce. The qubit is not shielded from its environment, it is hidden from its environment. The information is stored in a way that the environment is effectively blind to. Physicists call this topological protection. The word topological refers to properties that are global rather than local. Properties that describe the overall structure of something rather than any particular feature of it. Think of the difference between a sphere and a donut. A sphere has no holes, a donut has one hole, no amount of smooth deformation. No stretching, squeezing, or bending short of tearing can change a sphere into a donut or a donut into a sphere. The number of holes is a topological property. It is globally defined, globally stable, and locally inaccessible. You cannot change it by poking one part of the surface. You have to rip the whole thing. Topological qubits encode quantum information in the same way. The logical state of the qubit is a topological property of the quantum system, not a local one. Local noise cannot access it because the information is not in any local feature. It is in the global structure. The protection is not something applied to the qubit from outside. A refrigerator keeping it cold. A shielding keeping electromagnetic fields out. An error correction code catching mistakes after they happen. The protection is intrinsic to what the qubit is. You have not built a fragile thing and then defended it. You have built a thing that is structurally robust in the same way that a topological property is structurally robust. In February 2025, Microsoft announced a chip called Majorana, one which they described as the first demonstration of topological qubits reliable enough to serve as a computing platform. The physics community received this announcement with a mixture of genuine excitement and carefully managed skepticism, both of which were completely justified. Microsoft has been working on this approach for over 20 years. They've invested substantial resources. They have also had previous experimental claims in this area, retracted under scrutiny from the broader community. Most notably a 2018 paper that was formally corrected and eventually retracted in 2021 after errors in the data analysis were identified. So, the field has reason to be careful. The 2025 announcement was more carefully documented, passed initial peer review, and came with more detailed supporting evidence. Independent verification was still underway at the time of this writing. The honest answer is that it looks promising. It is not yet confirmed to the standard the field requires, and the history of this particular research program counsels patience before celebration. But if it works, the implications change the entire timeline. A topological qubit requires far fewer physical components per logical qubit than superconducting approaches. Instead of thousands to one, overhead you might get 10-1 or better. A processor with 1000 topological qubits could in principle deliver the logical computational power of 1,000,000+ superconducting physical qubits. The engineering path to practically useful fault-tolerant quantum computing shortens by orders of magnitude. The hardware that is currently projected to require decades and millions of physical qubits might become achievable within years and thousands. But step back from the engineering for a moment, because the deeper point here is philosophical and it connects directly to everything else in this story. Topological qubits represent a different relationship between information and physics than anything we have built before. In every classical system, information has a location. This electron is here. This magnetic domain is oriented this way. This transistor is in this state. Information occupies a place in space that is so fundamental to how we think about physical systems that we barely notice we are assuming it. In topological quantum systems, information has no location. It is in the relationship between places. It is in the global structure. It is real, verifiable, readable, and usable. You can extract it and compute with it, but you cannot point to where it is. There is nowhere for it to be. If you've been following this whole story carefully, that description should sound familiar because it is structurally identical to the description of how quantum computation works across parallel branches of reality in Deutsch's framework. In both cases, the information is real but non-local. In both cases, the protection comes from the global structure rather than any local feature. In both cases, you interact with the output without being able to observe the substrate directly. You get the answer. You cannot watch it being computed. Whether that structural parallel is merely formal, or whether it points at something deeper about the nature of quantum information and where it actually lives, is a question that is very much open. But the question is becoming harder to wave away. The information is real. It has no location. And the machines that exploit it are becoming more powerful every year. Part 14. The simulation argument is no longer abstract. In 2003, an Oxford philosopher named Nick Bostenram published a paper that most scientists read, found mildly interesting, and then quietly filed away under Not My Department. The paper was titled, Are You Living in a Computer Simulation? And it presented what became known as the simulation trilemma. The argument was clean and logical. One of three things must be true. Either virtually all civilizations capable of running detailed simulations of conscious beings go extinct before they get the chance to do so, or virtually all technologically mature civilizations, for whatever reason, simply have no interest in running such simulations. Or if neither of those things is true, the sheer number of simulated realities would so vastly outnumber base reality that we're almost certainly living in one right now. The math is straightforward probability theory. If simulations are possible and civilizations run them, then simulated minds outnumber real ones by an astronomical margin, and the odds favour you being one of the simulated ones. The argument attracted enormous popular attention. It made for great dinner party conversation, but for most working scientists, it stayed comfortably in the realm of philosophy. An interesting thought experiment about possibilities rather than a scientific hypothesis about actualities. There was no experiment you could run, no prediction you could test, no way to falsify it, so it sat there fascinating and inert for 2 decades, and then quantum computing happened and the conversation changed in a way that most people have not fully caught up with yet. Quantum computing does not make the simulation argument easier to dismiss. It makes it harder. Not because it brings us closer to building simulations ourselves, although that question is also worth sitting with, but because it fundamentally changes what we now know about the physical requirements for simulating a universe like ours. And what it reveals is that simulating quantum reality is not just harder than simulating classical reality, it is incomparably harder. The difference is not a matter of degree, it is a matter of kind. Richard Feynman, in a lecture he gave in 1982 that helped plant the seed for the entire field of quantum computing, made this observation with characteristic directness. He pointed out that simulating the time evolution of a quantum system of n particles on a classical computer requires resources that scale exponentially in n. Every particle you add to the system roughly doubles the computational cost of simulating it. A system of 300 particles requires a classical simulation with a state space larger than the number of atoms in the observable universe. You cannot do it. Not with more processes, not with more memory, not with more time. The mathematics simply does not permit it. You cannot efficiently simulate quantum mechanics on a classical computer because the state space of quantum mechanics is too large to fit inside any classical physical system. This is the same exponential scaling problem we've already encountered from the other direction. Quantum computers can access exponentially large state spaces precisely because they are quantum. And simulating quantum computers on classical hardware requires exponentially large resources for exactly the same reason. The two facts are mirror images of each other, and together they carry an implication that is genuinely uncomfortable once you follow it all the way through. Here it is stated plainly: if our universe contains genuine quantum mechanics, not merely statistical uncertainty, not just a convenient mathematical formalism, but real superposition and real entanglement of the kind confirmed by the Bell experiments and demonstrated by the Misha satellite over 1,200 kilometers of open sky. Then any computational substrate running a simulation of our universe would have to be a quantum computer or something with equivalent capability. A classical computer, regardless of how large or how fast, cannot efficiently simulate quantum reality. It cannot fake entanglement. It cannot reproduce the correlations that violate Bell inequalities with a local deterministic computation underneath. If we are in a simulation, the simulator is not a classical machine. The simulator is quantum. And now here is where it gets genuinely strange. We have established through decades of Bell experiments, culminating in the loophole-free tests of 2015 and honoured with the Nobel Prize, in 2022 that our universe does not have local hidden variables. There is no classical layer underneath the quantum behaviour, no deeper deterministic reality that just looks random and non-local from where we are standing. Any simulation that produces the quantum statistics we observe, the exact correlations that violate Bell inequalities by the margins that every experiment has confirmed, must genuinely instantiate quantum processes. It cannot produce them as an output of something classically simpler underneath. The physics rules that out. The simulation, if it exists, is not running quantum mechanics as a clever illusion on top of classical mechanics. It is actually doing quantum mechanics all the way down with no shortcuts. Now combine that with what we discussed earlier about quantum computation and parallel universes. In David Deutsch's framework, quantum computation works because it distributes its processing across parallel branches of reality. The resources that make quantum computing possible are not contained within any single branch of any single universe. They are spread across the wave function. If that framework is correct and the evidence from machines like Google Willow is disturbingly consistent with it, then a quantum simulator powerful enough to run our universe would itself require resources from parallel branches of reality. You cannot have a quantum simulation without a quantum simulator, and a quantum simulator is not a simpler or more mundane thing than the universe it simulates. In some frameworks, it is the same kind of thing, just described from a different level. The mystery does not dissolve when you move up a level. It reproduces itself identically at the new level. Think about what that does to the original simulation argument. Boston's version assumed something crucial: a clear hierarchy between the simulator and the simulated. Base reality is the real one. The simulation is the copy. The simulator is more fundamental, more powerful, operating from outside. That hierarchy is what makes the argument feel like it has stakes. If we are simulated, we are somehow less real, less fundamental, running inside something else that is more real. Quantum mechanics dissolves that hierarchy. If the simulator must be quantum, and if quantum computation requires multiverse-level resources, then the simulator must itself be embedded in something as large and as strange as a multiverse. The simulator is not standing outside reality operating a simple program. The simulator is in all the ways that matter physically as embedded in quantum. Strangers as we are, the clear boundary between the real and the simulated starts to look like a distinction without a difference. There is a further constraint that makes this even more striking. If we are in a simulation, the Bell experiments tell us that the simulation cannot be taking shortcuts on quantum correlations. Every entangled pair of particles in our universe, in every laboratory, in every physics experiment ever run, is maintaining correlations that cannot be produced by any local computation. There is no cheaper way to generate these correlations. The simulation would have to maintain genuine non-local quantum correlations across the entire spatial and temporal extent of the observable universe in real time without any loopholes, because we've tested for the loopholes and found none. That is not a modest computational requirement. That is an extraordinary one. Either the simulator commands resources that make our entire observable universe look like a rounding error, or the distinction between what is doing the simulating and what is being simulated has broken down entirely, and what we are calling the simulation and what we are calling the simulator are in the most physically meaningful sense the same kind of thing. What Boston Ram assumed was that simulated reality is less real than base reality. Quantum mechanics suggests that assumption cannot be maintained. Whatever structure is generating the quantum correlations we observe. Whether you call it the universal wave function, the multiverse, the information substrate, the simulator, or something, we do not have a word for yet. That structure is not simpler or more familiar or more classical than the universe it produces. It is at least as strange, and the evidence suggests it is stranger. We have not found a flaw beneath the stranges. Every time we look for one, we find more strangers instead. And here is the part that stays with me when I think about this carefully. We have in building quantum computers accidentally constructed instruments that push against this boundary, not from the outside, from the inside. We are, if we are simulated, building devices inside the simulation that appear to be accessing the computational substrate of the simulation itself. Devices that draw on resources no single classical branch of reality can provide. Devices that produce outputs which, if you take the physics seriously, require either a multiverse or a simulator that is itself a multiverse. Whether we are in a simulation is a question science cannot answer yet. Maybe it never can, but whether we have built a device capable of probing the structure of whatever is underneath reality, that question is starting to look considerably less rhetorical than it did 10 years ago. The machines are running, the outputs are real, and whatever they are touching when they compute it is not nothing. Part 15. The quiet possibility. No one wants to say. Let us bring all the threads together now, not to resolve them. They do not resolve. Not yet. Maybe not ever. But to look at them laid alongside each other and see what shape they make. We started with a machine. Sycamore completed a calculation in 200 seconds that would take classical hardware 10,000 years. Willow demonstrated that adding more qubits stabilizes rather than destabilizes the computation, violating every engineering intuition we have built up over centuries of working with complex systems. These are not interpretations or theories. They are experimental results published in peer-reviewed journals. Reproducible and confirmed, we followed the mathematics to its conclusion. A quantum computer of modest size 300 qubits would simultaneously inhabit a number of states larger than the total number of atoms in the observable universe. The information being processed cannot be stored in any physical substrate within a single instance of reality. This is not an engineering limitation, it is an arithmetic one. The numbers do not fit. We met David Deutsch, who in 1985 made this argument formally and concluded that quantum computation requires the resources of parallel universes. We met Hugh Everett, who 30 years earlier had formulated the physical framework that Deutsch was drawing on the many worlds interpretation in which the wave function never collapses and all outcomes are real in parallel branches. We watched both of them be largely ignored, and we noted that the hardware being built in 2024 fits their predictions better than any alternative. We watched the Nobel Committee award physics' highest honor to the experimentalists who proved that local, hidden variable theories are wrong, that there is no classical reality underneath. The quantum won. No hidden variables carrying pre-existing answers. The universe at its most fundamental level is not classical. It is not deterministic and local, and the correlations between entangled particles are real, non-local, and not mediated by any classical mechanism. We watched a satellite maintain quantum entanglement across 1,200 kilometers of atmosphere, confirming that entanglement is not a laboratory curiosity, but a global phenomenon that operates at scales relevant to real infrastructure. We encountered the ER equals EPR conjecture, suggesting that entanglement and geometry are the same thing, that space itself emerges from quantum connections and that a quantum computer may be at some level constructing and navigating the geometry of a space that underlies the one we can see. We met John Wheeler and followed his from bit idea to Landau's principle and the experimental confirmation that information eraser has a physical cost, that information is physical, that the substrate of reality may be formational rather than material. We followed that to the holographic principle and the suggestion that the three-dimensional world we experience is a projection of information encoded on a two-dimensional boundary. We came back to Earth and saw that governments and financial institutions are already preparing for a post-quantum world, replacing encryption standards and protecting future data from machines that do not exist yet. Because the people who understand this field best believe the threat is coming, and they're not willing to wait. We saw that quantum hardware is converging with artificial intelligence in ways that will produce systems doubly opaque to human understanding. We saw Microsoft's gamble on topological qubits which should protect quantum information by encoding it in non-local geometric structure rather than in any local physical property. And we ended up at the simulation argument and found that quantum mechanics makes it harder to dismiss. Not because it confirms we're in a simulation, but because it reveals that any substrate capable of generating our universe must itself be doing something as strange and as non-class as what quantum mechanics describes. What do all of these threads have in common? They all point at the same possibility from different directions using different tools. The possibility that reality at its most fundamental level is not what classical physics told us. It was not a collection of local determinate classical objects moving through space according to fixed rules. Something stranger, something whose full description requires a mathematical space larger than the observable universe, something that maintains non-local correlations without classical signals, something that produces computation that cannot be hosted by any single physical instantiation of matter. Now, what are the options? There are essentially three. The first option is that quantum mechanics as we currently understand it is incomplete, that there is a deeper as yet undiscovered layer of physics that explains all of the non-class behavior classically, that the exponential state space is an artifact of the mathematical formalism rather than a description of physical reality. That entanglement is real, but will eventually be explained by a local mechanism we have not found yet. This is the option that Einstein preferred. It is the option that Bell's theorem and the subsequent experiments have made extremely difficult to defend. The loophole-free Bell tests have been done. The experimental exits from local realism are closed. This option requires that the replacement theory preserve all of quantum mechanics predictions while having a completely different underlying structure, and no one has come close to building such a theory. The second option is that quantum mechanics is correct and complete, and that the physical interpretation of what it describes is genuinely non-class. That superposition, entanglement, and the exponential state space are real features of physical reality, not artifacts. That the computation in quantum computers genuinely accesses resources that no classical physical system within a single universe can provide. That Deutsch and Everett were in the most important sense right. The wave function branches. The branches are real, and quantum computation works because it is distributed across them. This is the option that the evidence taken at face value most directly supports. It is also the most philosophically disorienting because it requires accepting that most of reality, the vast majority of quantum branches, is permanently inaccessible to us running in parallel without any possibility of interaction, and that we are at every moment one branch among an uncountable infinity of others. The third option is that there is something new, a framework we do not yet have, a physics that is neither classical nor quantum in the current sense, something that resolves the measurement problem, explains the entanglement, accounts for the computational resources, and tells us clearly and unambiguously what is actually happening when a quantum computer runs. This is the option most working physicists would probably prefer. It would be science making its normal move. When the existing frameworks break down, build a better one. But there is no candidate theory. There is no compelling proposal that most physicists agree solves the problem. The measurement problem is 60 years old and no closer to resolution than when it was first named. The interpretations multiply, but none commands consensus. The honest answer, the one that requires intellectual courage to say plainly, is this: we have built machines whose operation we cannot fully explain. We can describe them, operate them, program them, and read their outputs. We cannot fully describe the physical substrate in which their computation occurs. The three options that remain all require either revising our picture of reality in ways we have not yet achieved, or accepting that reality is more profoundly strange than any previous generation of humans has had to grapple with. And there is something peculiar and moving about that. Every generation believes to some extent that it is living at the edge of human knowledge. Most generations are wrong. The things they thought were mysteries turned out to have mundane explanations. But there are moments, not many, but real, when humanity stands in front of something that genuinely does not fit, something that resists every effort to reduce it to familiar terms, something that insists on being taken on its own terms or not at all. Quantum mechanics has been that thing since 1927. Quantum computing has made it impossible to defer the question to future theorists because the machines are here now. They're running now. They're producing results now that exceed the physical resources of the observable universe. They are exploiting correlations that are non-local, robust and unexplained. They are demonstrating stability that should not exist. They are doing computation that cannot be classically simulated, and they are getting better at it every year. You might find this frightening. There is a version of it that is frightening. The idea that the most powerful computing technology ever built is operating on principles we do not understand, using resources we cannot identify in a physical substrate we cannot directly observe. That is a reasonable thing to find unsettling. The power is real even if the explanation is incomplete. The consequences for encryption, for AI, for science, for our picture of reality are real, even if the interpretation is contested. But there is another way to hold the same facts to find in them not fear, but the specific, particular quality of wonder that comes from standing at the genuine edge of knowledge. Every piece of evidence we've reviewed in this story points at the same conclusion. We have built something that accesses a level of reality that our best physics tells us is there but cannot fully describe. We have built a tool that is in some sense larger than the universe it operates in. We built it without knowing exactly what we were building. We built it before we understood where its power came from. And it works. There is a long tradition in the history of science of tools outrunning theories. We used fire for 300,000 years before we understood combustion. We used bridges for millennia before we could do structural engineering. We developed anesthesia before we understood neuroscience. In each case, the practical capability preceded the theoretical understanding, and the theoretical understanding eventually followed, changed by the existence of the thing that should not have worked but did. Quantum computers are that kind of thing. We built them. They run. We do not know. Not with confidence, not with consensus, not with any single framework that all physicists agree on why they run. We do not know where the computation happens. We do not know what physical reality is hosting the information. We do not know if the parallel branches are real, or if the information layer is primary, or if space-time is emergent from entanglement, or if we have built the first device that directly probes the structure of a simulation. What we know is that the machine works, and the question of why it works. The real why, the one that requires a complete and satisfying physical picture, remains open. Not just theoretically open, experimentally open. There are experiments being designed right now at laboratories in the United States, China, Europe, and elsewhere, probing the relationship between entanglement and space-time geometry, testing the predictions of quantum gravity candidates, looking for evidence of the informational structure that Wheeler intuited. The answer is not here yet, but the question has never been more precisely posed, and the machines that are posing it are getting more powerful every year. We are as a species standing at a very specific and historically unusual moment. We have built a device that our best theories say should not be possible in a single universe. We have confirmed experimentally that the assumptions required to dismiss that conclusion are wrong. We have built inadvertently what might be the first instrument in history capable of probing the structure of reality at the level where classical physics ends and something stranger begins. We did not set out to do this. We set out to build a faster computer. We got that. We also got a window into something that has no name yet, no agreed interpretation, no comfortable explanation, in refrigerators colder than the space between galaxies. We are running computations that span more states than there are atoms in the observable universe. We're doing it right now. The machines are running. The outputs are real. We just do not know where the computation is happening. And that question, honestly, fully with all of its implications, is the most important open question in science. Not because of what the answer might do for technology, though it will do a great deal, but because the answer, when it comes, will tell us what reality is, not what it is made of in some superficial chemical sense, but what it fundamentally is. What kind of thing exists? How many branches there are? Whether space is built from quantum connections, whether information is the ground floor of being, whether the universe is in the deepest possible sense a computation. The machine works. We just don't know where